The vast universe hides nothing yet remains filled with countless mesmerizing enigmas. Among these mysteries, black holes are undoubtedly one of the most mysterious and fascinating entities. They frequently appear in science fiction, such as the Gargantua black hole in Interstellar that swallows everything in its path. These objects are portrayed as distorters of time and potential gateways for interstellar travel, sparking our endless imagination. However, a black hole is not merely a product of fiction, it is a physical reality predicted by general relativity. It represents the most extreme gravitational field in the cosmos, a product of space-time being utterly warped. Our understanding of black holes has evolved from the early, vague concept of dark stars to the precise predictions of Einstein, and finally to the breakthrough of capturing the first actual image using the Event Horizon Telescope. Tonight, we will dive deep into the nature, types, and formation mechanisms of black holes, as well as their profound impact on the universe. We will also analyze the latest observational results and frontier theories, hoping to peel back the veil of mystery and understand the most incredible existence in the cosmos. The story is long, so let us journey into it together. Before we begin, remember to like and share. What exactly is a black hole? This seems like a simple yet incredibly complex question. At its most fundamental level, a black hole is a region in space where gravity is so intense that not even light can escape. To understand this, we must return to Einstein's general relativity. In this framework, gravity is no longer just a simple force as Newton described, but rather the curvature of space-time itself. Imagine placing a bowling ball on a taut trampoline. The fabric curves downward, and any marble rolling nearby will follow the curve of that depression. This is an intuitive visualization of gravity warping space-time. A black hole, then, is like a bottomless pit formed when the trampoline is infinitely stretched and torn. When the mass of an object is so extremely concentrated that the resulting gravity warps surrounding space-time to the limit, it forms an inescapable boundary known as the event horizon. The event horizon is the surface of the black hole, but it is not a solid surface like those we see in daily life. Instead, it is a one-way boundary for information. Once this boundary is crossed, neither matter nor light can escape the gravitational grip of the black hole, and no information can ever be transmitted back to us. This is precisely why a black hole is black. Light is completely swallowed, and nothing can reflect back to our eyes. Inside the event horizon, theory suggests the existence of a point called the singularity. The singularity is a point of infinite density and zero volume where all our current laws of physics, including general relativity itself, break down. The singularity represents a massive challenge for physicists, suggesting that we need a deeper theory, such as quantum gravity, to truly understand the core secrets of black holes. Black holes in the universe are not all the same, they come in various sizes and play different cosmic roles. The most common type is the stellar mass black hole, which is the inevitable end product of a massive star's life. When a star much heavier than our Sun exhausts its nuclear fuel, the outward radiation pressure can no longer resist its own powerful gravity, leading to a violent gravitational collapse. This process is often accompanied by a cataclysmic supernova explosion. The outer layers of the star are blasted into space, while the core continues to collapse inward under its own weight. If the remaining mass of the stellar core is large enough, exceeding approximately 2 to 3 times the mass of the Sun, a threshold known as the Tolman-Oppenheimer-Fokoff limit, then no known force can stop the collapse, ultimately forming a stellar mass black hole. It is estimated that hundreds of millions of such black holes exist in our Milky Way. Most remain silent and invisible, and we only detect them indirectly when they are part of a binary system, pulling matter from a companion star and emitting X-rays from an accretion disk. Even more massive than these are the supermassive black holes, which serve as the hearts of galaxies. Shockingly, almost every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center, with masses ranging from millions to billions of times that of the Sun. For instance, Sagittarius A star at the center of the Milky Way is about 4 million times the mass of our Sun. The formation of supermassive black holes remains a major mystery in astronomy. How did they grow to such scales so quickly in the early universe? Some theories suggest they originated from seed black holes formed by the direct collapse of massive gas clouds, or through the gradual merging of many smaller black holes during galaxy formation. These giants are not merely passive observers, they are closely linked to the evolution of their host galaxies. For example, the M-sigma relation reveals a tight correlation between the mass of a central black hole and the velocity dispersion of stars in the galaxy's bulge. This suggests a feedback mechanism where the growth of the black hole and the evolution of the galaxy influence each other, together shaping the destiny of the system. Between stellar mass and supermassive black holes, there exists a missing link known as intermediate mass black holes. Their masses typically range from hundreds to hundreds of thousands of solar masses. Finding these is a great challenge because they lack the abundance of stellar mass black holes and the active galactic signatures of supermassive ones. However, their existence is crucial for understanding how the largest black holes form. Possible formation paths include multiple mergers of stellar black holes within globular clusters or the direct collapse of dense gas clouds in the early universe. Recently, gravitational wave observatories have detected signals potentially originating from the merger of intermediate mass black holes, providing new clues for finding these missing giants. Beyond these observed types, theory also suggests the existence of primordial black holes. These are thought to have formed in the ultra-early universe shortly after the Big Bang, created by the direct collapse of high-density fluctuations. Their masses could range from the scale of an atomic nucleus to that of asteroids or stars. If they exist, they could have a profound impact, with some theories suggesting they might even account for a portion of dark matter. To date, however, primordial black holes remain theoretical, and we await conclusive observational evidence. Future gravitational wave detectors and other astronomical tools may eventually reveal their secrets, helping us understand the origin and evolution of the universe more comprehensively. Though black holes are mysterious, they are not entirely lawless. Physicist John Wheeler once used poetic language to describe their simplicity, stating that black holes have no hair. This no-hair theorem means that once a black hole is formed and stabilized, all the complex history of its formation and its material composition are erased. Only a few basic physical quantities remains observable from the outside. These are the three hairs of a black hole: mass, angular momentum or spin, and electric charge. Mass is the most central attribute, as it directly determines the size of the event horizon. The greater the mass, the larger the horizon. Next is angular momentum, which describes the spin of the black hole. Almost all celestial bodies rotate, and black holes are no exception. A rotating black hole is called a Kerr black hole, and its spin warps surrounding space-time in an incredible way, creating a phenomenon known as frame dragging. Much like a whirlpool drags the surrounding water, the rotation of a black hole pulls the very fabric of space-time along with it. As for electric charge, while theoretically possible, black holes in the actual universe are expected to be electrically neutral, as any excess charge would quickly attract opposite charges to neutralize it. Therefore, For most black holes we study, mass and spin are the two most important observable properties. While black holes are famous for devouring matter, they are far from being passive cosmic vacuum cleaners. Instead, many are among the most active and powerful energy sources in the universe. When matter, such as gas or dust from a nearby star, is drawn in by a black hole's gravity, it does not fall straight in. Because of angular momentum, this matter forms a fast-rotating, flattened structure called an accretion disk. Within this disk, matter collides and experiences friction under the influence of gravity and magnetic fields, causing temperatures to soar to millions or even billions of Kelvin. At these extreme temperatures, the matter emits intense X-rays and gamma rays, making the accretion disk one of the brightest and highest energy objects in the cosmos. By observing this high-energy radiation, we can indirectly detect black holes and study their properties. Even more spectacular are the relativistic jets. Some black holes, especially supermassive ones actively accreting matter, eject two incredibly bright, high-speed beams of particles from their poles. These jets extend for millions of light-years at near light speeds, acting like giant cosmic searchlights. Their exact formation is still an active area of research, but it is generally believed to involve the powerful magnetic fields within the accretion disk, which accelerate and launch part of the matter along the black hole's spin axis. These jets carry immense energy and momentum, significantly influencing the gas distribution and star formation of the host galaxy. They can heat the galactic gas and suppress the birth of new stars, thereby regulating the galaxy's growth. Galaxies with such active accretion disks and jets are known as active galactic nuclei, or AGN, including quasars and Seyfert galaxies. Their massive energy output is fueled entirely by the voracious behavior of the central black hole. Another startling characteristic of black holes is that they are not eternal. In 1974, Stephen Hawking proposed a revolutionary theory: black holes evaporate by radiating particles. This phenomenon, known as Hawking radiation, introduced quantum mechanics into black hole physics for the first time. According to quantum mechanics, pairs of virtual particles, a particle and an antiparticle, are constantly being created and annihilated in a vacuum. Normally, they cancel each other out instantly. However, near the event horizon, one particle may fall into the black hole while the other escapes into space with positive energy. To a distant observer, this looks as if the black hole is continuously emitting particles and losing mass. The intensity of Hawking radiation is inversely proportional to the black hole's mass. Smaller black holes evaporate faster, meaning micro-black holes would vanish almost instantly. In contrast, for stellar or supermassive black holes, the evaporation time far exceeds the current age of the universe. For example, a black hole with the mass of our Sun would take 10 to the power of 67 years to fully evaporate. Although this effect is negligible for the black holes we observe today, it has had a profound impact on theoretical physics, linking general relativity, quantum mechanics, and thermodynamics. It also led to the famous black hole information paradox, which asks whether information falling into a black hole is lost forever, challenging the fundamental principle of information conservation in quantum mechanics. This remains a central debate in physics today. Black holes grow not only by accreting matter but also by merging. Binary black hole systems are common in the universe, evolving from pairs of massive stars or forming during galaxy mergers where central supermassive black holes draw near one another. As two black holes orbit and approach each other, their orbits shrink in a spiral dance, eventually resulting in a violent collision and merger. This process is one of the most energetic events in the universe, creating massive ripples in space-time that travel outward at the speed of light, These are gravitational waves. Einstein predicted these waves in general relativity, but because they are so incredibly weak, they weren't directly detected until 2015. The Laser Interferometer Gravitational Wave Observatory, or LIGO, captured the signal from the merger of two stellar mass black holes, an event known as GW 150914. This marked the dawn of gravitational wave astronomy. The waveform of a gravitational wave contains rich information about the masses, spins, and distances of the merging black holes, acting like a recording of the event's sound. Through these signals, we can reconstruct the physical process of the merger. Black hole mergers are not just sources of gravitational waves, they are also a primary way black holes grow. For supermassive black holes, galaxy mergers drive these collisions, serving as a key mechanism for both galactic evolution and black hole growth. Understanding these physical properties is essential for revealing the sources of cosmic energy, the formation of galaxies, and the mysteries of space-time itself. Detecting a black hole is like searching for an invisible ghost in a pitch-black room. Since black holes themselves do not emit or reflect light, we cannot see them directly. For a long time, scientists could only infer their existence through indirect evidence. One primary method is observing the powerful gravitational influence a black hole exerts on its surroundings. At the center of the Milky Way lies a supermassive black hole called Sagittarius A star. While we cannot see it directly, astronomers using the Very Large Telescope in Chile have spent decades tracking a cluster of stars surrounding it. The orbits of these stars are extraordinary, they move at high speeds around an invisible, massive object. One star, named S2, travels at thousands of kilometers per second in a sharp elliptical orbit, coming within only 120 astronomical units of the center. Using the laws of universal gravitation, scientists calculated that only an object with a mass of 4 million suns concentrated in a tiny region could bind these stars in such orbits. This provides powerful evidence for the existence of Sagittarius A star. This method of inferring a black hole's presence by observing the Doppler effect and spectral line broadening of nearby stars has become a classic case in indirect detection. Beyond stellar motions, X-ray and gamma-ray observations also reveal black hole tracks. As mentioned, matter falling into an accretion disk becomes extremely hot due to friction and compression, emitting intense radiation. These signals are strong enough to be detected by space-based telescopes like the Chandra X-ray Observatory. In X-ray binary systems, we see a normal star orbiting an invisible, compact companion. As matter falls into the companion, it produces strong X-ray bursts. By analyzing the timing and spectrum of these signals, scientists can determine the mass of the compact object. If it exceeds the neutron star limit of about 2 to 3 solar masses, it is almost certainly a stellar mass black hole. Furthermore, active galaxies and quasars exhibit incredibly bright centers across the entire electromagnetic spectrum. Their cores are believed to be supermassive black holes devouring vast amounts of matter, with their accretion disks and jets serving as the most powerful energy sources in the universe. Radio telescopes observing these massive relativistic jets provide direct evidence of black hole activity. However, all of this remained indirect until 2015, when black hole detection experienced a revolutionary leap. For the first time, we heard the sound of black holes by directly detecting gravitational waves. These ripples in space-time, created by the acceleration of massive objects, were captured by LIGO's giant L-shaped vacuum arms using laser interferometry. On September 14, 2015, LIGO detected a signal from 1.3 billion light-years away. the waveform perfectly matched the theoretical model of two stellar mass black holes merging. This discovery, designated GW150914, not only confirmed the existence of gravitational waves but also provided the first direct proof of black hole mergers and binary black hole systems. Since then, a global network of detectors has captured dozens of such events, allowing us to analyze frequencies, amplitudes, and durations to unlock the secrets of the dark universe. Scientists can infer critical information such as the mass and spin of merging black holes, along with the immense energy lost during these collisions. It is like listening to a symphony from the deepest reaches of space, opening a brand new window for us to view the cosmos. The rise of gravitational wave astronomy allows us to explore the most violent events in the universe in unprecedented ways. If gravitational waves are the sounds of black holes, then the Event Horizon Telescope, or EHT, has provided the vision, allowing us to see the actual silhouette of a black hole. The EHT is not a single telescope but a global network of radio observatories. By precisely synchronizing and combining data from telescopes scattered across continents from Hawaii and Arizona to Mexico, Chile, Spain, and even the South Pole, scientists have effectively created a virtual telescope the size of the Earth itself. This technology achieves an angular resolution so high that it could distinguish an orange on the surface of the Moon from here on Earth. The primary goal of the EHT is to capture images of the region near the event horizon, specifically the black hole shadow, a dark area formed by light rays being bent by extreme gravity. In April of 2019, the EHT released the first ever image of a black hole, the supermassive giant at the center of the galaxy M87. This image revealed a bright, ring-like structure surrounding a clear, dark shadow. This ring is known as the photon ring, formed by light from the accretion disk being severely warped by gravity, while the central shadow represents the region beyond the event horizon where light is swallowed. This historic photograph not only visually confirmed the existence of black holes but also served as a precise validation of general relativity under extreme conditions. This was followed in 2022 by a second image of Sagittarius A star at the center of our own Milky Way. Although smaller and more dynamic, making it a greater challenge to capture, the EHT team successfully revealed its bright ring and central shadow, confirming once and for all that a supermassive black hole resides at the heart of our galaxy. These breakthroughs are massive leaps in our journey, providing direct visual evidence and precious data to help us understand the extreme physical environments surrounding these celestial giants. Black holes are not isolated ghosts in the void, they are active architects of cosmic evolution. Supermassive black holes and their host galaxies share a strange, symbiotic relationship. We now know that almost every large galaxy harbors a giant black hole at its core. Astronomers have discovered a surprising correlation between the mass of these black holes and the movement of stars within their galaxies, suggesting a feedback mechanism that links black hole growth with galactic formation. When a central black hole becomes active and begins devouring gas and dust, it releases enormous amounts of energy in the form of intense radiation and high-speed jets. This energy can heat up galactic gas or even blow it away entirely, suppressing the birth of new stars. This negative feedback maintains the ecological balance within a galaxy. Conversely, in some cases, black hole activity can trigger gas compression and actually promote star formation, known as positive feedback. This complex cycle of interaction shapes the diversity of galaxies we see today. When galaxies collide, their central black holes eventually merge in the most powerful events in the universe, releasing massive gravitational waves. These mergers act as catalysts, stirring up gas and dust, triggering new rounds of star formation, and activating new jets. On an even grander scale, primordial black holes from the early universe might even account for dark matter, that mysterious substance that makes up most of the universe's mass but remains invisible to our light-based telescopes. Furthermore, the intense radiation from early black holes likely played a role in the reionization of the cosmos, clearing the neutral hydrogen fog and making the universe transparent. While concepts like wormholes and time travel remain largely in the realm of science fiction due to their theoretical instability, the gravitational effects of black holes do cause real-time dilation. Near a massive black hole, time flows significantly slower than it does far away, a phenomenon that serves as the scientific foundation for many epic space stories. Our study of black holes also touches upon the most profound unsolved mysteries in physics, such as the black hole information paradox. When matter falls into a black hole, the information it carries appears to vanish, which contradicts the fundamental principles of quantum mechanics stating that information can never be destroyed. The introduction of Hawking radiation made this even more complex, as it suggests black holes eventually evaporate and disappear completely. To solve this, physicists have proposed bold ideas like the holographic principle, which suggests that the information of the entire three-dimensional universe might be stored on a two-dimensional boundary, much like a hologram. These deep theoretical questions use black holes as extreme laboratories, forcing us to rethink the laws of physics. Looking forward, the future of astronomy lies in multi-messenger observations, combining gravitational waves, electromagnetic radiation, and even neutrinos to gain a complete picture of the dark universe. New generations of space-based detectors like LISA will allow us to hear the mergers of the largest black holes and perhaps even the echoes of the Big Bang itself. These efforts are not just about satisfying curiosity, they are about expanding the boundaries of human knowledge. Black holes challenge our understanding of space, time, and reality, serving as cosmic beacons that guide us toward a unified theory of everything. They remind us that there is still so much to discover, and every breakthrough is a testament to human ingenuity and our eternal quest for truth. As we gaze into the dark abyss of a black hole, we are not just looking at a graveyard of matter, but at the light of human reason illuminating the furthest reaches of the unknown. That concludes our journey into the shadows for today. May you have peaceful dreams and a wonderful day ahead. See you next time.